session. He's Juan Pedro Mellado. I think he's the most difficult one to present because he's been in so many different places. So he did his degree in aerospace engineering at the Polytechnic University of Madrid. Later on, he did the PhD at UC San Diego, working on DNS of turbulent flows and these sort of complicated things. And then, and this is the difficult part, you went to the German Space Agency, right? Space or Aerospace Agency.
At some moment.
At some point, right? Then you were at the... Oh, you told me that yesterday, but I forgot, so...
I was here and there in Germany.
Here and there, okay. In Germany, many different places. And now currently he's working at the Max Planck Institute for Meteorology. So he's going to talk about an interesting topic on the dynamics of clouds.
Okay, so, thank you and good morning, everybody. Yeah, so... Yep. Control L.
Control Apple.
Control Apple?
No, Apple, I mean like in the Apple, control is like this.
Okay.
This weird key.
Thank you. So, yeah, I'm going to talk about some things that we are doing currently there in Hamburg, just to give a brief introduction to the ideas that we are developing. And I'm going to focus on these two ideas that you have here in the title. On the one hand, the atmospheric boundary layer, and in particular one region of it, which is the upper part where turbulence is occurring. And maybe the best way to introduce it is simply whenever we travel by plane in the descent, there is always a moment in which it gets bumpy, the plane gets shaky, and we know that we don't have to panic. And the only thing that is happening is that we are entering in the atmospheric boundary layer, and this is simply what I try to portray here. What you have in the lower panel is a cross sections through one of the simulations with which we are currently working. The plane is not part of the simulation, it's just for reference purposes. And what you see here is simply a very clear distinction between the lower part of the atmosphere, the one that is in contact with the surface, that is what we call the atmospheric boundary layer, and it is very often in a turbulent state, and the upper part of the troposphere, what we call the free troposphere, and it is clearly non-turbulent in the sense you can have motions, but those motions are non-vertical. If you want, they are smooth and gently. And then the transition between these two regions is the so-called entrainment zone, and there is where I want to focus today. Very often you cannot see it because what you see here is the gradient of the scalar that is provoking the buoyancy. So if you plot the scalar, you don't really see it that clearly, except when you have clouds. Very often you have these low-level stratiform clouds. This in particular is in front of the Canary Island. And what you see here is precisely the top of the atmospheric boundary layer. And it's really like an ocean, okay? Like an ocean of clouds, and has different properties very similar to the ocean, and I'm going to talk about them later. And this is the problem we want to understand, because in climate research and in weather numerical prediction also, this type of problems where clouds play a dominant role are difficult to reproduce, and difficult meaning really that the uncertainty in the models is of order 1. The sensitivity of certain aspects is undetermined down to the sign. Some of the models say it is a positive feedback, some of the models say it is negative feedback. So this is the driver. This is the driving question, if you want. So what I'm going to do in this talk is, first I'm going to introduce a bit more the details of these two concepts that I have presented so far, and then what I'm going to do is to tell a little bit about two particular cases. First, the one without the cloud, which is the easiest, if you want, and the point is to have a reference very clearly characterized so that we can see the effects of the clouds. And then I'm going to talk a little bit about what are the processes introduced by the clouds and how they complicate the nature of mixing there in this entrainment zone and an entrainment process in the end. Very good. So this is from a typical textbook in atmospheric flows and atmospheric turbulence. And what you have is simply the description of the atmospheric boundary layer as it varies during one day, okay? From noon to noon, in the vertical axis, you just simply have the height. And what you have is simply the sketch of the atmospheric boundary layer. The height of the boundary layer depends very much on the time of the day, the seasons, and so on. But let's say it varies between a few hundreds of meters and 1 or 2 kilometers. So what happens is that at noon, you have imagine the sun on top of you. You don't have that many clouds, so you heat up the ground very strongly. That can be the conditions in Castilla in summertime. And then what you have is simply next to the surface, you have relatively warm air that is buoyant, and that tends to go up, and then you just simply form this turbulent state that we have seen before, and that is simply pure convection. Then you form on the top this entrainment zone that I have already described before, and that goes on until the sun sets down. When the sun sets down, then you don't have the warming, this shortwave radiation from the sun. But we always have the radiative cooling from the planet. We are always radiating energy. So it cools down. The surface really cools down. And then what happens is that next to the ground, the opposite happens. Now you have relatively colder, heavy, stably stratified, and you simply grow a stable boundary layer here. And on top of it, you have simply what is remaining from the previous day, that is decaying turbulence, if you want. And that goes on until the following day. The sun rises, and then you develop a convective boundary layer that grows through this stable boundary layer, the residual. And in the summer, since you have more day than night, then it keeps growing day after day, and in the winter, the opposite. So this is more or less the framework where we are moving. And the top is this entrainment zone, this transition region. And this is simply a zoom on this transition region. This is work that one of the PhD students is doing. The first half of the talk is really her work. And what you have here is the same as before. You have the cross-section through this three-dimensional domain. Again, it is the scalar of the temperature, if you want, or the buoyancy, whatever you prefer to think about. And then what we have emphasized here is the entrainment zone. It's simply the upper part of the atmospheric boundary layer. And what you see is simply the so-called turbulence interface, in the sense that you have very clear, sharp, and relatively narrow transition from this lower part, where you have this lamellar structure with small scales, that is a turbulent part, in the sense that you have vorticity. And then across it, you enter in the free troposphere, where you don't have these strong vertical motions. You can have a little bit of vorticity because the gravity waves that you have there are rotational, but there's really a sharp change in the magnitude of the vorticity. And this is really a complicated 3D surface, varying in time, and different people is studying different details of the small scale aspects of this transition. Here I'm going to talk more about the bulk of it, and the main reason is that we still don't know what are, for instance, the characteristic scales that describe the bulk of these regions. It's really very difficult to get into the small scale details of this turbulence interface that I referred to before, when we don't even know what are the scales we have to compare them with. Okay? So it's a little bit in its infancy, in the sense that here, what is different from engineering maybe is that buoyancy plays a role, and therefore you have this continuous interplay between kinetic energy, potential energy, and the possibility of waves. But let's go on, because I have it here. Exactly, I forgot. So as I said, first you have this transition, this distinction between the turbulence and the non-turbulence part based on the vorticity or the vorticity fluctuation. But in this particular case, where buoyancy plays a role in the entrainment zone, everything gets complicated. This is driving me crazy. Okay, gets more complicated, because then part of the kinetic energy goes into waves. You can have radiation of waves upwards, or the formation of waves in this inversion that you form horizontally transported. Part of it goes into the potential energy, and then part of this potential energy can be recovered. It's available potential energy, but part of it is lost, in the sense that when you mix, when you homogenize the stratifying agent, that energy is lost, and you cannot recover it for potential mixing later. And on top of that, all that is dry. On top of that, you put the clouds. And then everything gets a bit messy, right? So the idea that we have there, the institute in which I am working now, is more climate research. And all the stuff that I'm going to talk about, For them, it's a small-scale turbulence. For some people here, it's not a small-scale turbulence because I'm going to be talking about the integral scales and things like that. But those are the scales that in this type of complex configurations are still not well understood. And the point is that from the perspective of climate models or numerical weather prediction or regional studies, all this is a small scale, it's turbulence, and for them it's turbulence, dissipative, period. You put a constant, dissipate something, mix something, and that's all you need to know. And it turns out that no, turbulence controls certain aspects of the mixing, fits back into the larger scales, and with the clouds it's very, very clear, because it controls if there is a cloud or if there is no cloud. And that changes the dynamics of the whole atmospheric boundary layer. Since we want to study turbulence, we don't use turbulence model. That is what we refer to as direct numerical simulation. That doesn't mean that we don't use, so far so good. We simplify the model, the physics, of course. We do not track the trajectory of each cloud droplet, and I will comment on that later. We use reaction, abstraction, or whatever. The only thing that we keep as clear as possible is the turbulence. And as I said, today I'm going to focus just on the role of this inversion and the entrainment across the upper part, the entrainment zone, without a cloud, and then a few aspects with the cloud. So no cloud, right? But possibly the most simple case is the one that you have here. This sketch, what you have is simply the surface, and we are representing the heating from the surface as a constant buoyancy flux. And you have a stratification of the atmosphere on top of it. It is this n squared. It's associated with some frequency, the buoyancy frequency. But what is important to know is simply that you have this constant slope in the variation of the buoyancy or the temperature, if you want. And as you hit the system from below, you develop this turbulent boundary layer that we have seen before. You homogenize, you mix, and you develop here this jump in buoyancy. So you have the near world region, the core part of the atmospheric boundary layer, the entrainment zone, and we have to, or we want to, characterize the entrainment zone. The typical question is, how fast does the entrainment zone moves upwards, for instance, and that is the mean entrainment velocity. But there are more things to it. What happens to the system as time goes by? Yeah, simply warm the atmospheric boundary. This is exactly the same as before, but this is from the real simulation. Before it was just a sketch. So you have here the background stratification. You just have the height, the mean buoyancy, some arbitrary units. As time goes by, you see that you increase the temperature or the buoyancy close to the wall, you mix it, and what you do is simply you mix the whole boundary layer and you warm the whole boundary layer. And what happens is that next or inside of the entrainment zone, this upper part, you always have this region of increased stratification. That is the reason for this name, the inversion. Is simply that the stratification there is higher, and it simply comes from the fact that these buoyant mixtures go farther than this level of neutral buoyancy, and since they have a lower buoyancy than this one, when you mix them, you have an intermediate value. But that is what people call the inversion. And then you start to study this problem in the sense that you want to predict it in time, and the best or one possible way to do that is you obtain the characteristic scales, and then in terms of these characteristic scales, you can normalize things, and you obtain some self-similar behavior, as we see in many different boundary layers. And here's where the problem starts, because you have different sets of characteristic scales. For again, height of the boundary layer, you can think of the following two possibilities. You can say, okay, what is important is the stratification on top, this buoyancy frequency n. That gives you some characteristic velocity and some characteristic buoyancy, the so-called encroachment variables. Some other can say, no, that is not important. What is important is the buoyancy flux. And with a height and a buoyancy flux, you have a characteristic velocity and a characteristic buoyancy. And sure enough, some things scale with these properties, with the convective scales, the second one, and some ones with the first one, with the encroachment. In particular, this mean temperature profile, or this mean buoyancy, follows very nicely the encroachment, in the sense that when you normalize the height and the buoyancy with the encroachment values, the two profiles that we obtained before, they just simply collapse on top of each other. And you obtain values of order 1 here for the characteristic buoyancy and heights. And I'm simply telling you that, okay, much of the dynamics of the system, at least for these quantities, is well characterized by these encroachment scales. And once you predict them as a function of time, you just need this normalized profile, and that's it. The problem is that if you look at the entrainment zone, and there is where we want to look at, it doesn't work. Here what you have is, again, quantities as a function of height that are related to the buoyancy. I think those are, in green, you have the mean gradient of the buoyancy. In red or pink, you have the buoyancy RMS, simply the intensity of the fluctuations around the mean that we have seen before. And in blue, you have the buoyancy flag, simply the covariance between the vertical velocity and the buoyancy deviation. And here we are using the same encroachment scales as before. Now what you see is that as a function of time, and that is represented here from the light color to the dark color, things keep changing. And it's simply telling us that the encroachment scales do not characterize the entrainment zone. So we have to look for a different scale. And in particular, here what proves useful is to look at some local scale. And what happens there, or the way we reason is simply that, as I introduced before, the entrainment zone is somehow a transition region between the upper free troposphere, where you have well-defined homogeneous in the horizontal properties, and the core of the boundary layer, which is also statistically homogeneous in the horizontal. And perpendicular to it, you have a strong variation of certain properties, like the mean buoyancy. So one possibility to characterize this sharp or fast variation of mean properties is the gradient thickness defined there at the point of maximum gradient. And indeed, if you use the gradient thickness and associated local properties for the buoyancy, for instance, you see that to leading order, the profiles tend to collapse more on top of each other. And it's simply indicating that, at least to leading order, these local quantities characterize better the dynamics of the entrainment zone. And the question then is, this is just introduced from looking at the statistical profiles. The question is then, what is the physical meaning of delta, if there is any physical meaning to delta, to this local scale? And there is. And it is associated with this idea of the penetration depth that is very, very easy. It's simply from parcel theory. And it is here a sketch. You just consider a parcel of fluid. And what you have to keep in mind is that you have a background stratified environment. This is what I have introduced already before in the sketch. So that the environmental buoyancy keeps increasing in height, so that the parcel of fluid, when it moves upwards and transport with itself its own buoyancy, feels a different background buoyancy at different heights. And the question is simply, what is the maximum height that you obtain for a given particular initial velocity? That's it. Okay, so it's really high school work. And you just obtain a value for this maximum height that you obtain based on this very, very simplistic mechanistic model, which is simply a ratio between the initial velocity and the background stratification. And indeed, delta, as introduced before, corresponds to this theoretical explanation. What we have here is we measure delta on the one hand. We have an expression for ZF, for the penetration depth. And if we plot the ratio as a function of time, this is the normalized time that I'm going to comment on now, you see that very rapidly it falls to a constant, meaning that one is a fraction of the other and it's of order 1, okay, of order 0.5. And what you have there is two different cases, a lower Reynolds number and a higher Reynolds number. The higher Reynolds number is the dark brown because we can run it shorter. And it's important because very often when you talk about these things to atmospheric people, they always say, okay, yeah, very cute, but that has nothing to do with reality, because in reality we have Reynolds numbers of 10 to the 6 or 10 to the 7, and here you are telling about 10 to the 3, 10 to the 4. But many of us know that certain things become independent of the Reynolds number, and that is the power of this Reynolds number similarity. And simply doing lab experiments or relatively small simulations, you can extrapolate to atmospheric conditions, and this is indeed the proof for it. I must say that the simulations are getting really to a point in which I wouldn't call them anymore small. This dark brown case, okay, Okay, Alvaro, I give up. The brown case there is equivalent to a tank, water tank, which is 6 meters by 6 meters with a boundary layer which is half a meter. So definitely it's not the atmospheric boundary layer, but compared to the lab experiment from the 80s, which was 1 meter by 1 meter, and the Reynolds number is 10 times higher as the lab. But still, it's sometimes difficult to convince these guys that this is useful. But okay, patience. And also we are able to really cover, in this normalized time, we can really cover the evolution of the convective boundary layer or a whole day. I don't want to go into the details, but these numbers that you have here are the ratio more or less between the boundary layer height and some measure, which is representative of the thickness of the entrainment zone on top. And between 10 and 20 is more or less what it gets to develop during one day. Yeah. Yeah, exactly. So the point is, to simply wrap a little bit with this dry case, the point is that simply we are getting the accuracy that is necessary to really find out this local scale in the entrainment zone. And in particular here, what we can see or what we can explain is that we have these local scales, delta, and those local scales represent the upper part of the entrainment zone, this Cij plus minus delta. Okay, and that is one sublayer, and that sits on top of the entrainment zone in the bulk, which is what people have been talking about before. And what is happening is that simply this upper part is acting as a transition between the free troposphere on top, non-turbulent, and the core of the atmospheric boundary layer, which is fully turbulent. And then you have certain properties that are characteristic to the upper sublayer, the lower sublayer. And what is funny is that as time goes by, both keep growing, but the upper one grows at a smaller rate than the entrainment zone, so that in relative terms, this keeps decreasing. So for the people in wall-bounded flows, this is kind of one temptation is to think about it as an upside version of the near wall region, and you have the delta, which is kind of similar to the roughness sublayer, and you have this transition into the bulk. And there are some work that try to really find some type of logarithmic or the corresponding scaling in this region. I don't think we have still accuracy to measure that, because it is really very, very heterogeneous compared to the channel flow or things like that. But there is some chance to look at things there. Anyhow, I'm talking too much. So you can then study different things. You can explain data from before, provide then the closure for the models that they use, and so on and so forth. But the idea is simply to focus on this idea that we can understand the mechanisms in this entrainment zone, because we are getting already the accuracy that is necessary. And particularly this penetration depth that we have shown describes the dry case. It's very useful also in the cloud case that I'm going to talk about now. The cloud. So why is it important in the first place? I've already shown you a picture in the beginning, in the introduction. That was these low-level stratiform clouds in front of the Canary Islands. Those are these stratocumulus clouds. And the point is that they are huge. This is the peninsula of California, the case, San Diego. And these are low-level clouds because you see that they delineate very nicely the coast of California. And they are huge because the horizontal extension is very large. This is 1,000 kilometers, the peninsula of California, more or less. And that's what makes them relevant, because these low-level clouds radiate incoming solar radiation, and they are important for the albedo, and they are so large that they really matter in the planet's radiative balance. And this other is on a broader scope is again California, Peninsula of California. This is the Hawaii Islands. I think this is 5 hours with the plane. And you see one of these decks here. And the point is, what I wanted to say here, that at some moment, as they are being distorted and moved towards the equator, at some moment they just simply dissipate. They break up. And that is what the models have really a lot of problems with. The models have to predict when and where they form, when and where they disappear, because they enter in this planet radiative balance. And that is what they don't get right, in the sense that different models, if there are 20, 25 models in the world being used for climate research, I don't know how many of them, but let's say half of them gives you a positive sign, in the sense that if you double CO2, they're going to increase, and the other half tells you, no, if you double CO2, they are going to decrease. And the reason why you have so much uncertainty is simply because it's complex. It's a complicated problem. The stratocumulus is simply sitting at the top of the atmospheric boundary layer, as I have introduced before. That problem in itself is interesting without a cloud, and now on top of it, you put there a cloud. Okay, so you have here the sketch, just representing the vertical structure. You have the surface, the cloud here, the boundary layer there that is varying between, I don't know, half a kilometer and 1 kilometer, and this inversion, this sharp variation of the temperature. And here is the moisture. You're on top of the ocean, so you are very moist here, and then you fall down to the tropospheric value. And we are talking about the entrainment zone, this little square here. This is, if you, Sally, how does it look like? If you zoom in there on a scale of a few tens of meters, what you see is really a two-layer system. You have a cloud beneath you, on top of you have the free troposphere, and this is just the liquid water to represent the cloud. And this is the buoyancy or the temperature. This is just a visualization of the case with the cloud in the same way as we were showing before. So you have a very strong variation of buoyancy between the cloud, the white values here, and the red values. And this increase in buoyancy is really happening on a small length scale. These are values for the simulation. So this is half a meter. In reality, this is a few tens of meters. And then this is further buoyancy anomaly that I'm going to discuss later. This is just to introduce more or less what is the picture. This is always three-dimensional simulations, okay? Just to describe more or less how does it look like when we look there. As I said, the cloud's complicated, but why the hell does it complicate? Well, because when you put a cloud there, so typically, up to now, I haven't saying that you form the atmospheric boundary layer because something happens in the surface, in the ground. You heat up, statically unstable, and you develop turbulence. When you put the cloud there, the cloud brings with it local processes that force the turbulence locally on scales of the order of the cloud top, let's say of the order of 10 meters, 20 meters. The first forcing that is dominant, or is believed to be dominant, is radiative cooling. As I said, all of us are radiating. Clouds are also radiating. These clouds are white, and they reflect much of the incoming shortwave radiation. So they cool down, whereas the top of the ocean is dark and warms up. The clouds cool down. And then what you have is in the upper part of the boundary layer, relatively heavy parcels of fluid that is, again, statically unstable, and they fall down and then agitate the whole boundary layer. So this type of marine boundary layers are not forced because the ground is warm, but because the top of the cloud is cool. And at night, they are the strongest. They are the most turbulent because you don't have this little of sun that is compensating. On top of it, then, you have evaporative cooling because you have droplets, and they evaporate. And when they evaporate, they cool down locally the mixture, and again, that contributes to form their parcels of fluid that are relatively heavier than the environment, and they fall down. On top of that, you can have the details of the droplet dynamics, what is called the microphysics, right? Do you have this aggregation or not? Does it settle or not? Or in particular, does it rain or not? Because in the end, the droplets have to collide to rain. In this particular type of cloud regimes, precipitation is not that important, but it happens, and sometimes you change the whole structure, but we are not looking at that. And then you can have wind, because as I said, you have the boundary layer, but then you have some advective wind that is displacing these things, and then what you form is at the top some kind of wind shear, and that can contribute to a different type of mixing there because of its interaction with the cloud. And the idea is simply to study different of these aspects separately and then bring them together step by step to get a more clear picture of what are the dominant processes here. And again, this is of the order of 10 meters, 20 meters. In typical simulations, in climate research, you don't even have a point here, a grid point. In numerical weather prediction or in large simulation, maybe you have 2, 3, but everything is dominated by the subgrid scale, by the turbulence model. So somehow we want to remove it. And today what I'm going to talk is simply just on evaporative cooling. Because that one, even if it is not the dominating mechanism, was, if you want, the biggest headache in the community. And the reason is the following. First, just to insist a bit more in the process. So whenever water evaporates, you cool down, you require the latent heat, and for instance, it happens at the surface of the ocean. You're continuously evaporating, and that means you cool down the upper layer of the ocean here, and that drives convection. The reason to introduce here the ocean is simply because if you look at the cloud deck from above, it's really much alike. The only difference is that the water is not in a continuous distribution, it's just in the form of droplets, but the essence is the same. You have a moist region and dry region here in blue, and as they evaporate, they cool down the mixture, and that drives convection upside down, and that is what I represent here. In black or in gray, from white to black, you have the temperature anomaly with respect to the cloud always. So that the blackest is the coldest. Okay? So you develop the coldest mixtures next to the interface because there is where you evaporate the most, and then you create simply turbulence, free convection. There is, however, it is a bit more subtle in the sense that on top of this evaporative cooling, we cannot forget that the upper free troposphere is warmer. Okay, you have this inversion. So yeah, sure, you are mixing and evaporating droplets, but as you are mixing, you are also warming the upper part of the cloud, here if you want, because the upper region is warmer. So you have just two competing effects. In this sketch, what I am representing is, for instance, some conserves the scalar that goes from the cloud to the free atmosphere, some enthalpy or total enthalpy if you want. And as a function of this mixing fraction here, I plot the buoyancy. In this thermodynamic space, what you see is that as you increase the conserved scalar, as you move upwards in the cloud towards the free troposphere, if evaporative cooling dominates, the buoyancy gets negative indeed, but at some moment you run out of droplets. So evaporative cooling stops, but the upper part is still warm. So then you just simply warm it up. In some, or for those thermodynamic conditions where this discontinuity, this change of behavior is such that you have this interval of mixtures that have negative buoyancy, that is so-called buoyancy reversal. And that brings me to this headache that I mentioned before. The headache is the following. They realize, okay, I have an instability there. I have the cloud, I have the free troposphere, and if I have this buoyancy reversal condition, the following can happen. Imagine that because of turbulence, I engulf some parcel of fluid from above, from the free troposphere here, I mark it in red. I engulf it, I entrain it, I move it into the turbulent region, which is in this case the cloud, and it starts to evaporate. And if it is in buoyancy reversal conditions, then you end up having there a parcel of fluid which is relatively colder, and it tends to fall down. It contributes to turbulence. And then the conjecture was that that can lead to a feedback mechanism in the sense that you create more turbulence, that turbulence can promote these mixing events that I have described before, and closing the loop, you can get into a runaway instability that creates, for instance, a hole, and that explains the rapid desiccation of the cloud. Remember when we saw this satellite picture, when we had the Hawaii Islands here and California Peninsula, there is a moment in which the cloud disappears. So maybe this is a reason why the cloud at some moment disappears. And people call it the cloud top entrainment instability. The problem is that they go there with the planes, they measure, and it doesn't work, in the sense that for these conditions, the cloud stays there. It does not disappear. The funny of it is that then they do large-scale simulations, and it happens. And then there was a discussion going on. Of course, the people doing the simulations, they say, the experiments are very bad, and the opposite. But you can ask the question, can it really lead to this runaway instability or not? And this is where we started working on the problem. And this is what I have been showing so far. This is coming out. This is again a cross-section, vertical cross-section across one of these simulations. And you have the cloud, the free troposphere, these negatively buoyant mixtures. And what you see is the cloud top remains flat. It is not broken. So there is no runaway instability as it is proposed. And the reason is why, and the reason is relatively straightforward, right? And it's simply that the cooling that you can get there from this evaporative cooling mechanism is very, very little. For typical thermodynamic conditions, you can get of the order of half a degree Celsius. Okay, sure, you lead into turbulence because there is nothing to stop it, and the length scales are very large. But from white to black is half a degree, and from white to blue is 10 degrees, which is the typical inversion that you have there. So it's simply, from that point of view, you already suspect that it's kind of weak, and I'm not going to penetrate across the inversive. Then you can do the linear stability analysis and so on. But in the end, the essence is simply the following: is you have this cooling that gives you a characteristic buoyancy, which is this negative peak in the thermodynamic space that we saw before. And that, in the end, is giving you what is the characteristic scale for this parcel of fluid that we have pictured before as green as being unstable. That gives you the time scale it takes for this parcel of fluid to fall down a length scale which is of the order of its size, right? As it falls down, sure, it tends to deform the inversion, dragging it, and the people were saying, yeah, that can create a hole. But the point is that the time scale that this guy requires to fall down an order of magnitude comparable to itself is much, much larger than the time scale that is required by this inversion to return to equilibrium, right? So you get a little oscillation there. Indeed, you have waves, but you don't make a hole. And that's it. I mean, so it cannot explain the breakup of the cloud. We can get a bit more into it, and for instance, we can try to estimate data that they measure in the field measurements when they go to the plane there. And that is the entrainment rate that I already mentioned before, is, for instance, what is the rate at which the cloud advances upwards, right? And we can make a question, let's see, what is this speed when you just have the evaporative cooling, right? And the way I see it is simply in the following. You have many processes, additive cooling, evaporative cooling, microphysics, wind, or whatever. And some people say, this is dominant. I say, okay, if you eliminate all the rest of the processes, and this is dominant, then what you obtain from this problem, even if it is very simplified, what you obtain from this problem will give you some quantification that is comparable to the observations, like the entrainment rate or the size of the inversion or things like that. And if it is not, then it is likely that this process is not the relevant one. Of course, you always have this nonlinear interaction between processes to keep in mind, but at least gives you an educated guess, as people like to say it. So this is what we did here. Again, you have the same plot, the same cross-section as before, but now we are plotting this scalar gradient that I mentioned before, and the reason is simply that it visualizes very nicely the layered structure of the system. And what we see is that indeed you have this convective region here, turbulence, and on top of it you really have a very clear, flat and thin stripe where you have a very sharp transition, but no turbulence. You have some fluctuations because it is still stratified, and you have waves. And that is, if you look at the equations, that is dominated by diffusion. So you end up having really a frying pan upside down, or a pot with boiling water. It's simply upside down in the sense that you have the near wall region, the diffusion sublayer here. The only problem is that this one keeps moving upwards in time, but in a frame of reference moving with that, it doesn't change. It's simply moving up. And then you look at the literature here that is there regarding this free convection or Rayleigh Penat, not frying pan, and you just find a model for the entrainment velocity. Don't pay attention to all the symbols. The point is simply that it works the same way. You simply say, okay, well, what is the thickness of this diffusion sublayer? Well, that is simply the thickness for which the two processes are comparable, very much like Alvaro was doing before. In this particular case, you have diffusion, and you have the gravity that is trying to pull down the mixtures that are next to this diffusion layer, simply pull them down, right? If it is very thick, diffusion is very small, and then the buoyancy is pulling very efficiently, and then it diminishes the thickness. And the opposite, if it is very thin, diffusion dominates, it thicks up before the parcel of fluid here, which is unstable, moves. And they are comparable for a particular value. That is the idea of this critical Rayleigh number. which is that, and when you plug it in, you can estimate the thickness or the entrainment velocity. That is what people typically look at in this type of problem. So we can measure the entrainment velocity from the simulation. We have this model here. We can form the ratio, as I mentioned before, for the penetration depth, and you plot it as a function of time for different cases. We work with data from field data and from field measurements, and then vary it. And then you see that for all of the cases, and as a function of time, you fall on top of each other and across a constant line. So it's simply indicating that this is a good estimate for this entrainment velocity. And the idea is simply that now you have an explicit formula to estimate what is the role, for instance, of buoyancy reversal in this case. And when you substitute the values, certainly you can say that it's turbulent, it's increasing mixing compared to diffusion, but the entrainment velocities, the mixing rates that you can explain are of the order of 0.2 millimeters per second, which is 1 order of magnitude smaller than what is being measured. So the point is that really buoyancy reversal per se, alone, without anything else, without interacting with anything beyond that evaporative cooling, is not capable of explaining dynamics of the entrainment zone. So you keep asking, what if I add the wind shear? What if we add radiation, right? And wind shear, for instance. Well, you have a physical model as before. You have this two-layer type of system, and then we can introduce a velocity difference in the horizontal, very much as you have in a shear layer or a stably stratified shear layer in particular. Notice that the physical model is simplified in the sense that I'm using a continuum description of the cloud. When the cloud is really formed by a population of droplets of the order of 10 microns, number density or whatever. But for the things that we are doing, this approach is, we believe, enough. So what happens when you introduce now just simply one control parameter more, which is delta U? Then what happens is what you have here, which is the picture that I have shown before. Now you have the shear, and when you introduce the shear, you eliminate this diffusion sublayer that you had before, because now the shear is really promoting turbulence and mixing there very efficiently. So you have a thicker entrainment zone, but it remains still flat. You have more mixing, because here you see really that you start to create these holes, and you have this maybe larger scale, more coherent type of a structure that is promoting these large plumes falling down. But in essence, it remains flat. Maybe it's more clear when you look at the gradients as before, simply because the gradient visualizes this inversion on top. Here, in terms of the entropy, remember this vorticity type of quantity that discriminates between turbulence and non-turbulence, or the enthalpy gradient. And then you see the convective part. Now, in the middle, you see very clearly this KH, this Kelvin-Helmholtz type of structures that are characteristic of an imposed mean shear. So we can ask why flat, right? Before it was flat because it was very weak. Now it's flat also because it's very weak, or what? And yes, indeed, that is what took us a few months. So it's very flat because evaporative cooling is very weak. And now delta U, the wind shear, dominates very much. And there is a lot of, or if you want, here this is what justifies what I'm saying. We can measure the velocity, the intensity of velocity fluctuations inside of a cloud, where you have the maximum velocity fluctuations, and comparing with delta U, the wind that is imposed at the top. And then you see that for different cases, as a function of time, it increases, but mildly, and it's just a few percent, 4 or 5%. So indeed, the dominant balance happens between delta U and delta V, the wind shear, and the delta V, the stratification or the inversion. And that is completely cloud-free physics. So you can look in the literature, and what you have is simply this stably stratified shear layer, and you know that you form this stably stratified shear layer, and you attain a characteristic thickness beyond which the mixing layer doesn't grow anymore, simply because the potential energy that is required is not there in the available kinetic energy. So you end up having this thickness, HS. So again, we have an analytical expression. We can measure H, the thickness of the entrainment zone, or of the inversion. We form the ratio as a function of time, and we see that without a cloud, you end up having values of order 1. This is diffusion, because for this case, it's kind of a low Reynolds number. And if you turn on the cloud physics, in this case, evaporative cooling, you fall down, but you remain at values of the order of 70%, right? So to lead in order, this scale, which is analytical, which is always nice, gives you at least one first characteristic scale for the length inside of the entrainment zone. And the picture that emerges is more or less this one, schematically. You have this stable stratified shear layer, we call it here the background shear area, beneath the turbulence. And the difference to the one before without the shear is that we have substituted the diffusion sublayer by the shear-dominated region. But the same is the same. You have a cloud boundary there. Turbulence tries to move upwards inside of this background inversion, that is this process of encroachment, and we want to obtain the entrainment velocity as before. And with the same idea, just to try to assess if it is important or not. And in particular here, if we can evaluate it explicitly as a function of delta U, better. And I'm not going to go into the details of it, but in the end, what you do is very often you look into the budget of the turbulent kinetic energy equation in this case. And it's varying in time, but it's quasi-steady. So to live in order, you have a dominant balance between the shear production there, where you have the shear-dominated region, the transfer of energy into potential, the buoyancy flux, and then dissipation. Dissipation is always there. And the buoyancy flux can be related by analyzing the mean buoyancy equation to the entrainment velocity, the rate at which the cloud or the turbulent region penetrates upwards. And in the end, it turns out that if you are able to estimate the characteristic velocity of the turbulence inside of the shear-dominated region, I call it U star, you are able to estimate the entrainment velocity. And there is where this idea of the penetration depth that we learn from the dry case kicks in. Because by looking at a picture, we have seen that you have a convection-dominated region, and that is the Earth of scaling, the one that you have here, that gives you an estimate for the turbulence intensity. And now you have to look into the shear-dominated region. And there, what matters is the Reynolds stress, in the sense that the production, the shear production, is dominating there, the formation of energy. And basically what you have there is then this inversion on top, where delta U dominates, is stereostratified, which is more or less the end that we had in the dry case. And beneath, you have the turbulence. In the dry case, we have learned that this turbulence penetrates, and the penetration distance that we have derived there as the ratio between W and N was characterizing the size of this penetration. So here we can do the same. We can use the same expression for delta in terms of the controlling parameters of the problems now. Another point is simply that you have this penetration and you have a vertical displacement of the order of delta across a region where you have a sustained mean velocity gradient, which is simply delta U divided by HS. And multiplying them, you have an estimate for U star, right? So we have some kind of heuristic model to obtain U star and W star characteristic scales, analytical expressions, and the same as before. We can measure the real velocities, in the sense we go there and measure the maximum URMS or the maximum WRMS from the simulations, and we form the relations with U star and W star as a function of time. And sure, for the different as a function of time, you get this flat behavior. For different cases, you tend to collapse one on top of each other, which is simply indicating that these scales, if not completely, because you see certainly deviations here, at least to live in order, tells you something about the dynamics of the system. Plug it in, and you have an explicit expression to simply reason if the interaction between evaporative cooling and mean shear is important or not. And here is where we can start to say, to make distinctions. If delta U, if the shear is very large, then yes, this is values typical from the field experiments that I have been using as a reference. So when you apply this theory to that case, you end up having entrainment velocities of what 3, which is comparable to the interval that they find in the measurement campaign, and thickness of the inversion, which are comparable to the measurement campaign. So it is telling us that the interaction of shear and evaporative cooling is relevant, but if you don't have a sustained shear, right, which happens sometimes when you have free convection conditions, then these, even though it is stronger than when you don't have the shear, you don't have a strong enough process to explain the data from the measurements. So something else is intervening, right? And you keep asking then, what if radiation, right? And that is what, this is one line of research there. Alberto de Lozar is working in that part of this problem, continuing it. this already tells us why the LES was having that many problems. Large scale simulation was enhancing, mixing spuriously because of the stability scale model, and that was just artificially cranking up the effect of evaporative cooling. Right? It is simply, if you have an additional mixing external for evaporative cooling, you increase very much the effect of evaporative cooling. That is the problem of large scale simulation. And that's it. I was trying to be a bit more descriptive and simply to show you what we are doing there from the point of view of turbulence. And the main idea, again, is simply to try to understand turbulence as part of the Earth system in the sense that it is beyond a dissipative process, and that's it. It enters into controlling the dynamics of certain parts, not all of them, but certain parts of the Earth system, very often in terms of the boundary layer. And as I said, really, supercomputers are opening now serious possibilities to study these type of problems, and the grand challenge is clearly clouds. What is the impact of clouds in the atmosphere? And with that, I thank you for your attention, and I'll take questions. Thank you.
Now the floor is open for questions. Is there any question? A question for the last speaker?
Lunchtime.
So you saw really nice, beautiful pictures at the beginning of the clouds, of the big scale clouds. Yeah. And I mean, of course, in the larger scale, you can see that it's kind of a plane, no, like a sea of clouds. Yeah. But you also see some patterns in a smaller scale. Yeah. Is that just because of the wind, or some?
No, there are patterns, and this is these large scale motions that you start to see in many different turbulent flows. In convection, these patterns are clearly these convection cells, right? In the sense that in this case they are upside down, so you see them as domes in the upper part. And simply because the parts that are, or in this case, you have the turbulent motion, right? When things, I'm going to explain it falling down. When things fall down and accelerate, right? Then by conservation of mass. You go there, it's always as easy as that, conservation of mass. So you strain, becomes thinner, you move horizontally, and that's why you have this cellular pattern that is dominant there. And that is what you see in these pictures. But it's true that when you have the wind, sometimes you see structures which are more kind of KH. In our case, we start to see alignments in 45 degrees that I've seen in shear layers and in jets, but not in this direction, but in the vertical. Also, the ones that are cool, that's why here somehow you have this cellular pattern here very clearly, okay? I don't know if these are 10 kilometers or something like that. But you have a very clear change in regimes here, and those are not very well understood. And also one that is funny is not here, but these are so-called closed cells, in the sense that the cell is cloudy in the middle. But when it rains, or drizzle, they call it there, it changes. And the cell is cloud-free, and the cloud concentrates just in the edges of it. Why? And when does it start to rain or not? Because there is where you have to involve microphysics, because then collision of droplets are important. So there is a whole world of it, and very few people are studying it from the point of view of turbulence, as many of us here do. They really take the perspective from the larger scale, keep increasing resolution, and see what happens. But the stuff that Oscar or Guillaume are doing from the small scales upwards, not that many people. And that's somehow what we want to explore. We cannot do everything, but some things are feasible.
Second question is, so talking about worlds. So
about
worlds. So it seems that it's a really robust mechanism that makes, let's say, this layer flat.
Yeah.
Either if you have fast wind, no wind. All that is mainly because evaporative cooling is weak, as you mentioned.
Yes, but it is. It comes from before. Here, if you notice, these are latitudes. These are the subtropics. The Canary Islands is the same, 20, 30 degrees latitude. So what happens there is that That's why here you have warm, dry air subsiding free troposphere. So what you have there is, in the atmosphere, you have upward motion in the equator, it goes up to the stratosphere, and then it goes down precisely at those latitudes. So in here, what you have is air that is coming from the upper troposphere downwards. It's really like the stagnation point that we study in fluid mechanics, and you form this constant boundary layer, in the viscous case. Okay, but it's very much like that. So you are pushing from above, and you are pushing with something that is warm and dry. But here is the opposite. In the ocean at those latitudes, it's relatively cold because you have upwelling. That's why they form in the eastern side of the ocean. You have the current that is going south, upwelling, and that decreases even more the temperature of the sea surface. And that's why here you have a temperature inversion which is of the order of 10 degrees. What you obtain in Castilla, when you have this convective boundary layer in the summer, the inversion you get there is 1, 2 degrees, nothing else. But here you really have 10. 10 degrees for these guys is like a rigid, solid wall.
So the question was more, what if you have a different world and you have, instead of water, you have a cloud of methane, for example?
I don't know, but I will look first.
I mean, of course,
I will look first at this large-scale motion of the atmosphere, right? And if then you have also oceans at these latitudes where you have this subsiding, then I will study this evaporative cooling, and then it's a matter of the latent heat. But water has quite a high latent heat. I don't know if you compare it with methane or something like that. Cannot tell you. But I would take that as a reference.
Yeah.
If it is smaller than the latent heat, it is even weaker. If it is larger, it's linearly proportional. So really, to duplicate this effect by 2, you have to multiply by 2 the latent heat. But the cases I have shown, I took the real case and I multiplied this constant by 2 just to cover a range of the parameter space. And it was kind of weak. In the end, the explanation, there was an explanation I didn't come. The explanation for this breakup, okay, it's as simple as that. Subsiding air, then the air turns down and moves towards the equator. Okay, Coriolis turns it there, the easterlies, and simply you move this guy over warmer and warmer water, right? So the inversion, you warm this, warmer, you reduce the inversion, and at some moment the inversion is so weak that you penetrate. Meaning you penetrate is you mix a cloud with the upper free troposphere, right? If this is 200 meters, if you are able to mix upwards 200 or 300 meters, then you distribute the cloud over warmer space, and you simply evaporate it. And there is some more fancy stuff there because you have some decoupling or whatever, but that's it. Yeah. Yeah,
So I have a question about the first study you did.
Yeah.
You showed some profiles that collapse when you use outer units, and then some other profiles that collapse with inner units. But I didn't see, or I missed, how did you define the inner units?
Yeah, here is the gradient thickness. For instance, in the shear layer, right? In the shear layer, you have the momentum thickness. Another possibility is the gradient thickness. You have the mean profile of the velocity. You look at the point of maximum gradient, and that gradient is the one that you use to define delta, the vorticity thickness, delta U divided by the maximum gradient. This is the equivalent, but for the buoyancy. The only difference is that you have to take into account that you have a linear profile in the upper pass. So you just have the maximum gradient, right? And then from this point of maximum gradient, you just define the height where you intersects the extension of the upper mean buoyancy. But in essence, is the vorticity gradient of the shear layer is what we used here. So it was very much it was simply, I knew that from the shear layer, and I tried it here. It was not, I didn't have the physical explanation came later, really.
In a sense, then, is a posteriori, not a priori.
A posteriori, the explanation, the physical explanation?
No, the definition of the one. You cannot do it a priori. Before doing the simulation, you cannot estimate the size of delta, right?
In the beginning, no. Now that we know it is the penetration depth, yes, because we know it is, right? We can say it is 0.5 of ZF. ZF is the penetration depth, N is a control parameter, and W is WRMS of the convective boundary layer. But that is well represented by the convection scale. And there's where we close, and it is predictive. Predictive a posteriori. Sounds very nicely, but it was not like that. There's always a bit of trial and error. I saw one of these, I was telling some talk about scientific method and so on, and they said a scientific method is not as cool as it looks. It's looking for a black cat in a dark room, and sometimes there is no black cat. So here we were looking around things from turbulence, and one worked, and then it makes sense, but it was not a happy idea.
Any more questions? Okay, so thank you very much to our last speaker of the morning. So the thing is, we have now some time for lunch, and we'll be back at 5 p.m. Spanish time. So that's like 8 p.m. US Pacific time, 4 hours less in Argentina. I mean, like, I don't know, everybody make the number. So it's 5 p.m. Spanish time. Okay, thank you very much.